Okay, well, it's 10 o'clock and we'll go ahead and get started. Thank you all for joining this next edition of the Long Coffee Break. My name is James Murphy. I'm a senior sales engineer here at Long. And today we're going to talk about where we're going with refrigerants. We're lucky enough to be joined with Philip Johnston. He's with Daikin Applied Americas. He's been with Daikin for about 20 years, and he's been in charge of our air terminal units, worked with the chiller group, and now he is a GM in charge of low GWP refrigerants. Thanks, Philip, and I'll let you start.
Hey, thanks very much, James. Welcome, everybody. Let's move on to the next slide then. So this is what we're going to cover here today, and rather than me simply reading the slide, ultimately, my hope is to translate better understanding to all of you about our path forward by looking at what's going on with regulations, legislation, and also suggesting certain alternatives for refrigerants. So on the left-hand side, what we're trying to show is there's this Kigali agreement, and that was basically an amendment to the Montreal Protocol. As of September, there were over 100 countries. They're probably at about 120 right now who have actually ratified the Kigali Amendment. On the right-hand side, what we're trying to show is the U.S. Climate Alliance member states, and that was formed a couple of years ago with the de facto leader being California. There are 24 states and Puerto Rico joined this alliance, and ultimately their goal was simply to honor the basic tenets of the Paris Agreement rather than just refrigerants. So big picture, anything to do with climate change. So you can see there potentially could be a huge patchwork of rules coming if we had just different states doing their own thing. So as such, AHRI, the US Chamber of Commerce, actually many stakeholders came together and negotiated and wrote the AIM Act that came through with signers from both the Republicans as well as the Democrats. And what's really new, in late December, it passed through Congress and was signed by President Trump. The AIM Act roughly aligns with the Kigali Amendment, but more specifically, it authorizes the EPA to manage HFC usage in all sectors. So not just air conditioning. And that means phasing down production and consumption of higher GWP refrigerants to 15% of a baseline by 2036 here in the United States. So looking at the code adoption process, this is a graphic that tries to highlight where we're at and what needs to happen. So ASHRAE standard 34, 15, and even the UL product standard called 6335-2-40, they are published and under constant revision for flammable refrigerants. And in particular, what we're talking about is class A2L refrigerants, which are going to become more common. I want to point out you must never retrofit a class 2L refrigerant into a class 1 system. It's not permitted by these standards, and it could prove very dangerous. So it's up to us as manufacturers and designers of systems to develop the necessary safeties into those products per these standards. Now, the US EPA also has what they call SNAP approval. To use any refrigerant in any sector, you need EPA SNAP approval for that applications. Several low GWP refrigerants have already been approved, and several are in the application stage. Moving on to model building codes, these must be rewritten and then adopted locally in either the state or a local municipality or county, depending on where you're based. In summary, no building codes today truly allow the use of flammables in direct systems over 3 kilograms per circuit. Below 3 kilograms per circuit, or 6.6 pounds, certain ones do allow use in those small systems. So as such, what you see is small PTACs, or even like room air conditioners. You can walk into your local home store and find window air conditioners using R32, which is an A2L, because they're very low charge quantities. When it comes to chillers, you have much more flexibility because they're installed in mechanical rooms and they're also installed outside. So current model codes allow the use of flammable refrigerants. It's just none are really being offered yet in the market. So looking at this slide, I want to point out that the direct global warming potential of the refrigerant itself from leaks, so that comes whether they're leaks in manufacturing, during operation, or at the end of life, isn't at all about the efficiency of the HVA system. So making a decision solely based on the GWP of the refrigerant is an incomplete argument. In reality, about 85% of the climate impact over the total life cycle of any HVAC system has to do with the efficiency of the equipment, because the electricity is mostly still produced in America from the burning of fossil fuels. So 85% roughly is the average. And it might differ from state to state, but that's kind of a good fit. So we have to think about efficiency if we really want to, minimize climate change. Let's move on. Looking at R123 alternatives, I just want to say the colors in the table on the right reflect two things. Red means worse performance than the incumbent. Green is better. Yellow means it's roughly the same, so within a couple of percent. So we're looking at R123 low pressure alternatives. R514A we feel is an interim refrigerant, even though it has an ultra low GWP of 2. It's low enough pressure, like 123, that it doesn't need ASME vessels. But if you don't like 123 now, then you won't like 514A, because it's a group B1 higher toxicity refrigerant. It has 3 to 5% lower capacity than R123 and a little bit less on efficiency. So it brings the total CO2 emissions up over the system life cycle as compared to 123 in a similar system. It also happens to be a blend. Blends are never as good as single components. Now, R1233ZD is an A1. It's ultra low GWP, and it's available today from a number of chiller manufacturers. And Daikin Applied will be doing the same over the next few years as products are developed. It has better capacity and comparable efficiency to R123, so it's really starting to take over around the world. So I believe that the future replacement or current replacement for low pressure chillers is R123ZD. When it comes to R134A, if you look at that table, you'd love to see a double green. If you can't get a double green, you'd love to see a double yellow. But we don't have that. So we just don't have really great alternatives to 134A in terms of capacity and efficiency. And we don't want to slide on efficiency, because emissions over the lifetime of the equipment exceed the direct emissions from refrigerant leaks. Now, if you look at 513A, which is out there today in the market by some manufacturers, you lose about 3 to 5% efficiency as compared to 134A. Because it sacrifices efficiency and has higher GWP than other options, life cycle energy consumption should be worse. So Daikin will bring chiller to markets with 513A probably over the next year, year and a half, but it's because it's a near drop-in to 134A, so it'll give customers that option. But it's probably a short-term solution because of that efficiency degradation. The only ultra-low GWP refrigerant that offers comparable efficiency is the A2L called R1234ZE down at the bottom. So it's nice that it's a single component. It happens to be an A2L, but you're able to produce a product that delivers on great efficiency. When it comes to blends, also blend ratios can change during service and maintenance. They could impact the class of the refrigerant potentially if they're not kept exact, and the performance of the unit. So we like single components. Now, if the market or our customers dictate that they don't like A2Ls, there is that 515A and 515B. 515B was simply developed by the same producer as A, where they added a little bit more of this 227EA into the blend. 227EA is a fire retardant. So it raises the GWP of the fluid to 292, but still pretty good, and has similar performance to the single component 1234ZE. So they just added enough of that fire retardant to squeeze it into the A1 category. Let's move on to the next slide. I'm going to talk about replacements for R410A. Now, It's estimated that over 120 million R32 units are already in use around the world. So it's having replaced R410A, and that's increasing by upwards of 25 million units per year and accelerating. The European residential market last year was already 37% R32, and it's forecasted that by 2023, 85% of the residential market will be R32. So the equipment that is using R32 around the world includes residential splits, room air conditioners, like window air conditioners, VRV/VRF, rooftop units, and chillers. So R32 has become the de facto standard to replace R410A for a number of reasons. So R32 is actually makes up 50% of R410A by mass. It's not a new refrigerant. Rather, it's a very trusted, very high performing refrigerant. So there's over 200,000 tons already being produced around the world. So to convert all R410A systems over to R32, chemical producers only need to double their production. For other low GWP blends, certain components are patented and their production processes are patented, and the production is very, very low. So there needs to be massive investment in producing those chemicals in a very short period of time. Because R32 is a commodity and availability, it can make a service tech's life much, much easier and an owner's life easier. Because it's a single component, it can also be more easily cleaned, which means better for reclaim purposes and therefore reused by customers over and over again. There's not a lot of reclaim going on with the blend R410A today. But if you look at the structure of the Kigali Amendment, where over time all refrigerants are going to be managed, like the production will be allocated, I think having a single component refrigerant where we are able to reuse those refrigerants over and over again is a really great step. Now, we also know that if you reclaim all those molecules, then they don't go into the atmosphere. So that's a good thing. Yeah, let's look at that next slide. This chart is for pure refrigerants only. It was developed by NIST and published. NIST was looking to find alternatives to replace R410A based on a number of factors. You see up in the right-hand side, only R32 has really great performance. I should say on the left-hand side, efficiency in terms of COP was normalized against 410A. And then on the horizontal axis, you see volumetric capacity normalized to 410A. So it was the only pure refrigerant or single component refrigerant they found that outperformed 410A. So low and medium pressure fluids like 1, 2, 3, 4, YF, and ZE, which are great in chillers, really don't work in 410A because of that capacity loss. It's at a 40% capacity to 410A, which means much, much bigger equipment and bigger compressors. Not too good. Now, any blends proposed to replace R410A are 400 series. So they're 2 carbon molecules, ethane-based, all with some temperature glide. And if you could click right now, James, there is a proposed refrigerant out there called 454B. It blends R32 with one of these 1, 2, 3, 4 YF. So it loses capacity and has similar efficiency to 410A. Chemical manufacturers are blending these things together with the HFOs to change performance, often trying to match 410A capacity and efficiency. So if an OEM chooses these blends, they probably have lower development costs, but they limit equipment performance as compared to pure single component R32. Next slide. So R32 does have excellent thermodynamic performance. So an OEM system engineer can develop more compact units at the same efficiency level using less materials, or alternatively, you can leverage that better thermodynamic efficiency of R32, slow down compressors, and push the efficiencies to new higher levels. That's pretty incredible. So for example, in our Daikin Applied Rebel inverter products and also in scroll compressor chillers on our test stands, we were able to slow the compressors to match our 410A capacity. And that yielded up to about a max 12% efficiency improvement than 410A. So that's really huge for the environment and really great for owners who really care about efficiency. Now, alternatively, with that R454B, because they lost a little bit of capacity with no real efficiency benefit versus 410A, we lost a little bit of capacity. So we had to speed up the compressors. So in turn, they drew more watts and we lost efficiency. Next slide. So in summary, if we were to look at these alternatives in the same way, there really are no ultra low GWP HFO refrigerants that don't completely change the cost or the economics of these products. So it's down to a pure single component R32 or blends that all contain large quantities of R32. Now you might wonder, what is this R466A? That's an A1, the GWP of 697. You see it's a 3-component blend and it has glide. It contains a relatively new for HVAC refrigerant called CF3I. The I is iodine made from seaweed. It's not readily or easily available. It's not produced in mass quantities, so it'll be quite expensive. Now, R466A, even though it's squeezed into the A1 category, has a room concentration limit, or RCL, in the same range as R32 or 454B. So you would still need to look at those calculations to make sure you can use it. That RCL is based on its toxicity, not based on its flammability. We question the stability of this refrigerant. That carbon iodine bond is very weak, and it can break down, forming acids within the system. It was first brought up in 2018 at the Kobe Symposium about these issues, and then there have been other publications since. So we have concerns for the ultimate reliability or durability of our equipment with this 3-component refrigerant. It also tends to have lower performance than 410A. So the GWP is 697 right now. Because it's a very heavy molecule, you need a lot of this refrigerant. You need upwards of 10 to 25% more charge than 410A. So if you add more charge to your HVAC units, there's more to leak. So we've termed something called effective GWP, when you normalize it to 410A. So it really sits around a GWP closer to 800 because of the needed refrigerant within the system. When you look at, if you click next, there's a disadvantage for R32 compared to 454B in that the direct GWP is higher at 677 versus 466. But because of that tremendous performance, you can use 20 to 40% less charge of R32 versus 410A. So it really has an effective GWP down below 500. So to us at Daikin Applied, we've announced that we're going to go with the commodity single component R32. It is the only solution that yields much better performance in terms of capacity or efficiency than 410A, and it's available, being used around the world, and should really work great long term as we develop new equipment to replace 410A. That's my summary. Thank you, James.
Great. Well, Philip, not to put you on the spot, but we're going to do a rapid fire kind of thing. 123, the replacement refrigerant that you see going forward is
1233ZD long term.
134A, the replacement refrigerant is?
Depends on 2 scenarios. I prefer single component 1234ZE, which is in class A2L. If customers want to use an A1, then there's that R515B, which is 90% 1234ZE.
And last, 410A?
If I wasn't clear, R32 all the way.
Okay.
Hands down, by far. We should have been using R32 for the last 20 years.
Thanks, Phil. I really appreciate it. Thank you all for joining us on this coffee break. Now's the fun time. We're going to list our prizes. Please join us next week when Bill Rohn's going to be talking about rooftop units with stripped down controls. Thanks so much for joining us, and we'll talk soon. Thanks.